All right, so let's start this lesson by looking at what we defined in the last section of Unit 1 as instantaneous slope. So we're going to just rework that out just because we need it to define a derivative correctly. It's very, very, very similar to what I'm going to talk about in this lesson, but I'm going to add a little twist to it that brings us fully into the realm of calculus. So over here on my blank sheet, let me clear that lower third. Let's talk about rates of change. So we did explain, let me get my blue pen, that when we want to find slope, we know we say the change in y over the change in x. That's something we've been doing for a very long time. We define that as taking, oops, I just turned my turned my pad and now I'm running back sideways. Let's undo that. It's just gonna offend the OCD among us. All right, so the change in y is where we take the y2 value and the y1 value, and we find the difference, and we divide it by the x2, the difference of the x2 and the x1 value. So that's old news. Then we said we can actually take that from being an average rate of change to being an instantaneous slope, to showing us the instantaneous slope at a point by, let's make a little squiggly line to divide it. If we were to say, let's find the limit of 2 points, we'll call one f of a and one very close to it called f of a plus h. So the x value would be a and a plus h. And so we would have f of a plus h is the second y value, and f of a is the first y value. And then the x values, x2 and x1, would be a plus h minus a. We could write that in parentheses, but we don't really need to because it doesn't change anything mathematically. And when we drop the parentheses, we see that this a and this minus a cancel. So actually, I could get rid of everything on the bottom and just leave h, since a minus a is 0. So we're taking the limit of f of a plus h minus f of a all over h, where h is approaching nothing. And the reason that that's important is because we're trying to find instantaneous slope, which means that we need to take 2 points where we're finding the average rate of change, and we want to bring those 2 points until so close that they're essentially the same point. That's where h is becoming essentially 0. We bring them so close so that we're not just finding the average slope for this section of a graph, but we're finding the instantaneous slope at that point. So that's what we discussed in the previous section. How does that relate to defining what a derivative, this first half of calculus, how do we use that to define what a derivative is? And how is it different? How is it the same? How is it different? Okay, I'm going to use a different color, but we'll see if we can leave this up and fit everything on here. So a derivative says we don't just want to find the rate of change, the slope, at one single point. A derivative is actually a function, which means we can have several inputs and several outputs, like actually infinitely many inputs and infinitely many corresponding outputs. So we don't want to just find the slope at one single point. We want a function that's actually going to help us define the rate of change or the slope at any point along a particular function or graph. So here's how we're going to do that. We're going to use the same exact equation that we have up here on the top right of your screen. Limit as h approaches 0 of f of a plus h minus f of a all over h. Same equation, except instead of choosing a point A, we're going to generalize it and say, let's find the function for any point x. And that's going to be it. That's the only difference between what we did at the end of Unit 1 and the beginning of Unit 2. Here's how we do this. We say, let's find the limit as h approaches 0 of f of x plus h. So instead of a, which a represented a single let me underline here, a single point, we're looking at x, which is going to give us any point along the line. So f of x plus h minus f of x all over h. And that, the function that this yields is called the derivative. We have now accomplished something very momentous in calculus. This is the official definition. Normally when we're defining a function, we want to say something like y equals all of this, right? Or f of x equals all of this, right? That's how we define a function, is by naming it. The problem is we can't use f of x or y to define a derivative because we're going to get it confused with the f of x that's inside the derivative, right? We can't name the function that we're using and the derivative with the same symbolism, or we're going to get really confused. So I was going to say calculus users have defined a few ways that we can label this, except that's probably not true. The founders of calculus and the mathematicians along the way have given us a few different symbolic ways of defining a derivative function. 4 ways that I'm going to show you here in this video. Let's go to a blank screen. So we know that a derivative is that whole limit as h goes to 0 of f of x plus h minus f of x all over h. That's what it is. But how do we symbolically label that with something like a y equals or a f of x equals? How do we do that? So let's look at our 4 different ways here. 1, 2, 3, and 4. Okay, the first and the most common way for us to define a derivative is by using y, because we know y is what we normally call a function. Like, that's the most generic way of calling a function, y equals. But if it's a derivative function, we're going to call it y prime. So it's just like when we say y equals, but it's going to say y prime equals blah, 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 right? Y prime. So that little mark at the top is meant to be a superscript. It's kind of like what we use to say it's an apostrophe, really. That's kind of what, well, sort of. It's a very plain, straight up and down. It's the same sort of notation we use to say, like, it's 5 feet, and instead of saying feet, we use a little like an apostrophe. So y prime means the derivative of a function. So that's pretty straightforward, simple. Another way that we can define it is by using as I'm doing this, I'm going to add in a 5th one too, because as I was about to do the 4, I changed my mind. So number 2, I'm going to say we can also be a little bit more specific, because you know how sometimes we have a lot of functions and we want to give them different names. So we might call it f of x, g of x, h of x, m of x, it doesn't matter. We can do the same thing. Just like y prime, we can say f prime of x. And what that means is it's the derivative of the function x. So actually, let's go back to our original screen over here. We're using here the function f that we're trying to find the derivative of, meaning trying to find the slope at any point along that function. Not just at one point, but any point along a specific function. What function? Well, in this case, we're going to be really vague and call it f. So what derivative are we finding here? We are finding f prime. So I will write, kind of over my picture here, f prime of x is equal to all this stuff. So this would be, if I were to use the function g of x plus h minus g of x all over h, which would be the same definition, just using g, the only thing I'd have to change is turn this into g prime of x. So this second method for defining a derivative is a little bit better than the first, because it allows us to have multiple derivatives of multiple functions and keep them all organized. F over here, g over here, h over here, and so on. Okay, still call it g prime of x. First one we call y prime, f prime of x. Okay, number 3. The third way that we talk about derivatives is using this symbolism, which, yeah, I'll keep it in the same color. We read this as dy dx. So you can actually write this out. We read it dy dx. Or the other way we could read it is the derivative of y with respect to x. With respect. It's a good thing I'm saying this out loud because that respect just got totally blurred out there. But so we can read this as dy dx, or we could read it as the derivative of y with respect to x. Now, why would we have, y prime, f prime of x, those two seem pretty straightforward. So why would we come up with something like dy dx, which frankly just seems a little bit confusing? Why add all these letters in? Well, the reason that this is such a valuable symbolic way of defining a derivative is because it shows us both the output and the input variable that we are concentrating on. And that becomes really important, say if we are dealing with functions that have a lot of variables. So maybe like a physics function, which we might have a whole different slew of variables that have meaning, like what is the time, what is the distance, what is the speed, what is the mass, like those sorts of equations we might want to find a derivative of, and we'll talk more about that later on in Unit 2. How are we going to know which variable we want to be the output and which one we want to be the input? Well, when we call it dy dx, or we later on can change those variables to whatever we want, although normally it's dy dx, we're able to see very quickly what that information means. And we do it the same way that we would say like y prime equals blah, 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 all this math stuff. We would say dy dx equals blah, 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 blah. So it's the same thing. We use it the same way, but it's just a slightly different way of labeling it. Okay, that is method 3. So let's go back to our list. We still have 4 and 5 since I added on that last one. Okay, number 4 is almost exactly the same. It's kind of like the difference between 1 and 2. You can also say something like df dx. Same labeling, same wording, but as you're probably expecting, the nice thing about this label is that it allows us to distinguish several different functions. So if I have f, g, and h, I want to know which derivative goes with which function. We need a way to keep that organized. So df dx would be an example, or dg dx, dh dx. It would all be the same pattern that you'd see there. Okay, 1, 2, 3, 4. Last way, and I'm gonna scoot this over a little bit so that it doesn't get squished, is to say the derivative with respect to x of some function. So the derivative with respect to x of some function, in this case f of x. So we reverse. Up here we said the derivative of y with respect to x. Here we're saying more the derivative with respect to x of the function. How is this important or even different from the other methods? Again, it's still the same. You'd say the derivative with respect to x of this function equals blah, 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 like that. This terminology allows us to see taking a derivative as an actual operation, a mathematical operation. So we know operations like addition, subtraction, multiplication, division, square roots, other types of roots, powers. So those are all mathematical operations. And we can take a function, like let's say we had f of x, and we can say, hey, let's take this whole function and take the square root of it. That shows me that I am operating on, not like a medical operation, but a mathematical operation on f of x. And taking a derivative is actually also an operation, same kind of idea. We are changing a function. So we could say we are going to perform the derivative operation on the function f of x. So those are, let me go back, those are our 5 different methods for defining a derivative. And again, I am taking the time to explain this so that when you are reading through a problem in your textbook, or you're reading about calculus either in your textbook or maybe a different resource that you have, all of these different definitions of a derivative are going to turn up, and you need to be able to recognize it and preferably be able to correctly read it as well. Because if you're reading it aloud to somebody who knows about mathematics, they're going to want to correct you if you say it the wrong way. So take a little bit of time to not just write these down in your notes, but also write down how to say them so that you can sound like a really amazing, qualified calculus student. Okay, that's all we're going to cover in topic 1. And in the topic 2 video for lesson 1, we are going to do one short example that shows us what exactly I mean by, say, doing the operation of taking the derivative. What do I mean by that? How does that look? And what kind of answers do we get? So we're going to do one example of that, and then we'll pick the rest up in class. So I hope you enjoy the information in topic 2.